Taipei 101, the world's tallest skyscraper. 508 meters of the most high-tech engineering and construction on the planet. Mixing ancient values with cutting-edge technology and taking the heart of Taiwan into the future. Designing and building the world's tallest skyscraper is no easy task. But here in Taipei, two of the most powerful forces of nature, earthquakes and typhoons, combine to make going super tall a super challenge.
I mean, any tall building in the world is a feat of engineering.
Using world-leading engineering and construction techniques, Taipei 101 not so much conquers nature, but outsmarts it.
This is the only super tall building in the world that's designed in a seismically active zone. This has never been done before, certainly not to this scale.
The result is a man-made marvel, a unique megastructure of unprecedented size, shape and technology, built to withstand the very worst that nature can dish out.
I, for one, I'm a structural engineer. If there's going to be an earthquake in Taipei, I want to be in this building. I mean, I'll choose this above all else.
And it's not just as a superstructure where Taipei 101 pushes the boundaries.
We are not only managing a building or a city of a city. I believe we are managing the symbol and landmark of Taiwan.
Taipei 101 is a benchmark of technological brilliance and innovation. A record-breaking megastructure that defies nature and puts the small island of Taiwan firmly amongst the giants of global industry. For as long as humans have been making buildings, those buildings have been getting taller. From the Empire State Building in 1931, Sears Tower in 1974, Central Plaza Hong Kong in 1992, to the recent Petronas Towers in Kuala Lumpur. Skyscrapers are buildings that go beyond functionality. They are symbols of prosperity and power, icons of wealth and industrial might.
If you're looking at the history of skyscrapers, really you begin in America, Chicago and New York are the classic cases. But in the last, let's say, 10, 15 years, Asia's really boomed with regards to the building of large structures.
In recent years, Asia has seen an explosion of mega-scale building and industry. The region now holds 8 of the world's 10 tallest buildings. And as modern construction methods and materials continue to improve, designers will continue to aim ever higher. Not because they have to, but because they can. Developer Harris Lin is one of the most powerful and successful businessmen in all of Taiwan. A member of a major construction dynasty, for him, Taipei 101 is the result of a lifelong ambition.
Since I was a boy, I have dreamt that one day I would build a great building, one which will benefit later generations for a very long time.
For Harris Lin, Taipei 101 is more than just a building. It's a statement on Taiwan, its people, and its future. A notice to the rest of the world that Taiwan has the technology, the industry, and the determination not just to join the giants of global industry, but to lead them.
There's no better way, really, of getting global attention than building these super tall buildings, particularly if it's the highest in the world.
Initially earmarked as the centerpiece for the growing and glitzy Qiangshan district known as Taipei's Manhattan, the primary goal for the building is to be the best, but not necessarily the tallest. Long-standing friend of Harris, architect C.P. Wang from C.Y. Lee & Associates, comes into the project in the early stages.
We started with 3 buildings, a 60-story building in the center and 2 smaller buildings that are about 20 stories for the different shareholders.
But plans quickly evolve as key investors clamor to have the building push up, not out. The planned 60 stories soon turns into 88. And with the mantle of the world's tallest a mere 13 floors away, the momentum becomes unstoppable.
We truly believed we could do it. That if we worked hard, we could make a building that was visible to the entire world.
But three factors combine to make this project not only the tallest and most visible in the world, but also one of the most difficult to build. Taipei City is an inhospitable place to build a skyscraper. Beneath the earth, a thick layer of soft clay demands uniquely designed foundations. While above ground, the threat of earthquakes and typhoons requires a level of engineering and construction never before achieved. If Harris Lin wants to make the tallest building in the world here, his engineers and builders will have to confront the power of the earth. Designing a structure flexible enough to resist an earthquake, but stiff enough to resist a typhoon. Contradictory requirements that until now have never been combined.
All these different mixtures of elements have to be blended almost superbly in order to make the building achievable.
The solution will combine two revolutionary systems. First, a braced megaframe joined to 8 super columns filled with a mixture of steel and concrete. And a tuned mass damper, a giant pendulum, the weight of 10,000 people, designed to oppose the effect of wind. The combination of these two concepts is groundbreaking.
I am very proud of it, and as architect, you don't get a lot of opportunity to work on something of this magnitude.
Construction will take 6 years, 2,000 workers at any one time, and 700,000 tons of the most advanced steel and concrete ever made.
These cost more than the national GDP of some countries.
Yet despite all the investment, ingenuity, and determination of humankind, the forces of nature can strike at any time, whether you're ready or not. Taipei 101 will be built to withstand earthquakes and typhoons, but it also needs to withstand the test of time. To be a true landmark, it must look unique. Its appearance mixes traditional Chinese icons, bamboo for strength and resilience, a pagoda for serenity, the perfect form of an open flower, and the luck and prosperity associated with the number 8.
We tried very hard to do something that we hope can represent the city, the island, as well as our culture.
The result is this: 508 meters tall, 101 floors from ground level. A building that looks completely unique, but soon proves challenging to build. Every major skyscraper in the world is a trade-off between what will look good and what will stand up.
For a tall building this height, you cannot escape in the practical matters. It has to work.
Taipei 101 will be the tallest skyscraper on Earth. And the forces on a building of this scale are truly immense. Gravity forces it down, while wind pushes it sideways. Existence is a tenuous balance between being strong enough to stay up, but not so heavy as to cause collapse. Most skyscrapers have exterior walls that are either straight up and down or sloping in. But Taipei 101's unique shape sees much of its exterior surface sloping out. Here at Evergreen Consulting, engineer Shaw Shi oversees plans that will translate Taipei 101's unique exterior into one of the strongest, lightest, and most resilient interiors ever made.
The shape of Taipei 101 is more complicated than regular tall buildings, because simple and straight lines will be easier to work with.
Aesthetically, Taipei 101 is broken into sections resembling a stem of bamboo. But similarities with this fast-growing superplant don't end here. Just like bamboo, the distinct structural sections of 101 strengthen and support the whole building. Each section operates as an independent unit, transferring the building's massive weight away from the outside of the building and into the middle. The result is a stronger, lighter, and more flexible tower. For CP Wang, this sort of lateral problem solving has been integral to the success of the project. Their aim is not just to be the highest, but to be their innovative best.
Let me put it this way, it's not like the Wright brothers when they invented the airplane. You know, today a lot of people knows how to build an airplane, but it's how good it is matters.
The design of Taipei 101 requires unique engineering to facilitate a unique shape. But the next challenge facing designers pushes this engineering to the limit. How to make the tallest building in the world stand up against two of the mightiest forces of nature in one of the most hazard-prone cities on Earth. Every year, the people and buildings of Taipei are under attack from two of nature's most primal and unstoppable phenomena.
When you put a tall building on an old secondary earthquake fault line, which runs nearby here, and in a place where you get significant typhoons, that just has major challenges.
The problem is that to resist wind, a building must be stiff. But to survive an earthquake, it must be flexible. Taipei 101 will have to be both.
This is the only super tall building in the world that's designed in a seismically active zone. This is really pushing engineer and construction boundaries right to the limit.
The island of Taiwan sits at the junction of two tectonic faults, where vast plates of the Earth's crust grind together, causing earthquakes. The entire island is unstable. Three smaller faults run directly under Taipei itself, causing hundreds of earthquakes every year. The effect of an earthquake on a giant skyscraper can be catastrophic. The entire building is shaken to its foundation as intense waves of energy from the Earth are transferred to every inch of the building structure. To withstand these shocks, the building needs to be flexible so it can move with a quake and not against it. If it's too stiff or brittle, it can break. Superficial damage like broken windows or walls can be repaired. But any damage to the internal steel framework of a building can be a disaster. As the tallest building in the world, Taipei 101 must be engineered to withstand major earthquakes. But just how major is something of a mystery. Geologist Dunstan Chen is one of the scientists charged with finding out the details.
This is when we make the first design, okay? We have to consider this fault. We know there's a fault somewhere here, but we don't know exactly where it is.
An investigation is launched involving some of Taiwan's leading geologists to find out where the fault is and how far it is from the Taipei 101 site. They need to establish if it's active and how they should deal with it. The results shock everyone.
Then we drill number 4. Okay, we encountered the fault. And this fault, actually, the gauge was around 10 meters thick. It's a huge one.
In most earthquakes, the closer the building is to a fault, the worse the impact. The fault found by Dunstan and his colleagues is not only huge, it's close. Only 200 meters away from the 101 construction site. 101 must be prepared to face the most extreme earthquake shocks imaginable. Here at the NECRI facility, scientists use a multi-dimensional shake table to simulate a variety of different earthquake scenarios. Scale models of different structural configurations are tested, and the information gained helps to design buildings that are better able to withstand the devastating impact of earthquakes. An earthquake shock delivers brutal vertical, horizontal, and twisting strain on a building. Every joint of every structural element is strained, and if there is one weak link, the whole lot can go. To keep 101 standing in a major earthquake, engineers develop a complex internal megastructure. The central core of the building is connected to 8 incredibly strong supercolumns by a network of horizontal outrigger trusses. The supercolumns act like a giant flexible spine, enabling the building to flex and move if it needs to, but not break. Although the idea of supercolumns has been used in other buildings before, the size of 101 takes this engineering to an entirely new level. But the threat of earthquakes isn't the only natural force that builders of Type A 101 have to worry about. Every summer, unstable equatorial air off the coast of Taiwan generates vicious typhoons that lash Taipei. These intense tropical storms, with winds of up to 200 kilometers per hour, can literally blow a building to pieces. But it's not just strong winds that designers of 101 have to worry about. The surface area of a skyscraper is so huge that even a small breeze can still have a major effect. As wind hits a building, it impacts in 2 ways. First, the exposed face of a building can be pushed by the wind like a giant invisible hand. But under certain conditions, the wind can generate pulsing vortexes on opposing sides of the structure. The vortexes begin to oscillate, exerting small but consistent pushes on alternating sides of the building, eventually causing it to sway. Like a child pumping their legs on a swing, each gust of wind adds energy. This swaying can be so severe that occupants of high-rise buildings can experience motion sickness. Normally, engineers can accommodate this problem by making the internal structure of a building stiff and rigid. But being stiff is exactly what designers don't want in the event of an earthquake. Can engineers of 101 design a building that is both stiff and flexible at the same time? For the project to go ahead, they have to. Type A 101 is so massive that finding ways to minimize the effects of wind is a vital element of its design. Engineers and scientists begin with the building's exterior. They find that by using re-entering or saw-toothed corners, the flow of wind around the building is drastically reduced.
The results of wind tunnel testing, the re-entering corners help to reduce the dynamic wind response by 30 to 40%.
Saw-toothed corners on a building hinder the formation and impact of the small wind vortexes that can cause it to sway. But just like the pumping of a child's legs on a swing, where each push adds energy to the last, even when the effective wind on a skyscraper is reduced, energy will continue to gather unless it's removed. It's not the size of the push that matters, it's the repetition. If engineers can find a way of canceling this accumulation of energy, then the building's contradictory requirements of strength and flexibility will finally be met.
Usually, a lot of tall buildings use so-called computer-controlled mass to do that function. In our case, I think our very smart engineers come up with this passive tune mass damper.
The passive damper on 101 uses a huge weight hanging from an upper floor to counter the effect of wind. As Taipei 101 sways in one direction, the tuned mass damper swings in the other, cancelling the buildup of energy and reducing the building's motion. Engineers of Taipei 101 have made the impossible possible, designing a building that is stiff enough to survive a typhoon, yet flexible enough to survive an earthquake. But although these ideas seem to work on paper, they are yet to be proven in practice. 101 is going to need a lot more than just new design to combat nature. It's going to need entirely new materials and construction methods as well. Taipei 101's unique megastructure and wind damper will make the building resist the impact of earthquakes and violent storms. But all of this engineering means nothing unless the giant building has a solid foundation on which to sit. Finding solid ground in Taipei is a lot harder than it sounds. Over hundreds of thousands of years, changing sea levels have filled the Taipei Basin with layers of soft, unstable silt and clay. In order for the tallest building in the world to remain standing, its foundations must penetrate through this layer, sometimes 60 meters thick, to find the solid bedrock below. Geotechnical engineers spend 8 months collecting core samples to analyze the soil on the building site. They find 3 distinct layers of soft sediment before finally reaching solid ground. This information helps designers to develop detailed plans for 101's foundation structure. Preparing the foundations takes 15 months and removes 700,000 tons of earth from the site. The foundation of a skyscraper is one of its most vital structural elements. It must distribute the building's enormous weight evenly below ground, at the same time creating a super strong base for the towering megastructure above.
That's the key point for the whole building, that the building can stand up into the sky.
To compensate for the inherently unstable ground of Taipei, 101's foundation is designed to literally pin the building to the deep layer of bedrock below. A 23,000 cubic meter concrete slab sits on top of a complex system of 382 reinforced concrete piles. These piles transfer the building's weight and structure deep into the bedrock, meaning 101 is more than just resting on the earth. It's fused to it. This unique foundation, combined with 101's mega frame and damper, give the building an extraordinary earthquake safety rating that exceeds even that of Taiwan's nuclear power plants.
Inside the 101, during earthquake, you wash out the falling particles, okay? Rather than worry about the falling of the building.
Taipei 101 will not just be one of the strongest and most stable buildings in Taiwan, but one of the strongest and most stable buildings in the world. Building on the main megastructure begins in September 1999.
If I look back, I feel it was more difficult than I expected. But I didn't feel that way when I was working and solving the problems every day.
This isn't a construction workforce, it's a construction army. Here at the Kaohsiung China Steel Plant, some of the most high-tech steel manufacturing techniques in the world are being used to build the various elements of 101's groundbreaking megastructure.
The basic idea of this building is so-called double tube. structures, which means we using the steel frame to create the outside tube, and then we using the steel frame and the concrete columns to create inner tubes.
The steel used in Taipei 101 needs to be soft enough to weld, hard enough to carry the building's awesome bulk, and pliable or bendy enough not to weaken or break if it's rattled by an earthquake. Each of these requirements demands a different type of steel, a complex chemical cocktail of carbon, alloy, and refined iron. More carbon makes it stronger, but too much and it becomes stiff, brittle, and hard to weld. The Kaohsiung plant develops 5 different kinds of steel for 101, each with a specific flex-to-strength ratio designed to suit its purpose and position in the building. The challenge for manufacturers is to make perfect steel into perfect components for 101 each time, every time, day after day. Starting with the raw materials, massive blast furnaces push out 10,000 kilogram ingots of refined steel. The ingots are near liquid hot, 1200 degrees Celsius. An elaborate system of hot rollers and purification baths torture and squeeze the giant blocks into 90mm thick flat plates. Precision, control, and consistency are crucial. Any imperfections mean weakness, and any weaknesses could be fatal for the mighty 101 megastructure. Patterns, ID numbers, and cutting are all controlled by computer. This plant uses more electricity every day than a small city. From start to finish, each super column box section takes 4 months to make. The final product is big enough to park a car in, weighs as much as 90 tons, and is as tall as a 2-story building. Each of 101's super columns will need more than 50 of these box sections. That's more than 400 for the entire building. The next challenge facing builders will be to put them together. The integrity of 101's megastructure requires the super columns to act as single units. But joining 30 90-ton box sections into one seamless unit has never been done before. Yet again, 101 will tread new ground. Ordinary welding techniques simply won't cope with the enormity and detail of the task. Every millimeter of every join requires absolute perfection. Teams of 6 welders work simultaneously. The entire girth of each join has to be heated for the welds to bind. The scale of the task is mind-blowing. Each join takes at least 14 hours to complete. That's nearly 2 years welding in the super columns alone. The high-strength steel and advanced welding techniques used in 101 super columns give the building a strong and flexible backbone built to withstand the shock waves of a severe earthquake. But dealing with the building's incredible weight demands an entirely different type of strength, one that steel alone cannot provide.
A building usually has 2 types of force, the tension force and the compression. And we all know steel works better for tension, and the concrete works better for compression.
The awesome weight or compression loading on the world's tallest structure would crush the super columns if they were hollow. But filling them with concrete to the 62nd floor combines the tensile strength of steel and the awesome compression strength of concrete. Making the system even more robust, engineers develop a concrete mix that is 60% stronger than normal. Concrete able to withstand an awesome 10,000 pounds per square inch of compression. The combined benefit of steel and concrete gives 101 the strongest, lightest, and most flexible backbone of any skyscraper on the planet. A backbone that is about to be put to the ultimate test. (2:52 p.m., March 31st, 2002). A magnitude 6.8 earthquake rocks northern Taiwan. The entire island is brought to its knees. And in Taipei, only 135 kilometers from the quake epicenter, over 100 houses are destroyed and at least 5 buildings collapse. The quake wreaks havoc on the construction site of 101. 2 purpose-built cranes topple 240 meters to the ground. 5 workers are killed and dozens more injured. A taxi driver fleeing his vehicle is crushed. Taipei is a disaster zone. All work on the building stops as aftershocks continue to strike. Insurance disputes rage, and engineers and surveyors check the massive building for hidden structural damage.
It was a big challenge for me at the time. The 9/11 attack had happened in the USA just before. And so our people and our investors began to question whether we needed such a tall building in Taipei.
The work ban continues, not just for days or weeks, but for 3 months. An earthquake, the very force 101 has been designed and built to survive, now threatens to destroy the building's future. Not physically, but financially. Morale plummets, and a dark cloud hangs over the project. Finally, in July 2002, the building surveyors give 101 a clean bill of health. The internal framework is intact, and once more, work can resume. But the victory is bittersweet. No scientific test could have proven so effectively that 101's mega frame can resist a severe earthquake. But no scientific test would have come at so great a cost. The notorious March 2002 earthquake has put 101's mega frame under the most extreme test imaginable. But as work resumes and the skyline of Taipei is increasingly dominated by 101, a geologist from a prestigious local university discovers a worrying combination of data. Although only one severe earthquake has struck Taipei since work on 101 began, there has also been an unusually high number of smaller ones. Taipei 101 might not just be the victim of recent quakes, it might be the cause.
When the second fair earthquake occurred again, almost in the same location, then I take it very serious to do some research work.
The fact that Taipei is a seismic hotspot and that 101 is built only 200 meters from a dormant fault line is common knowledge. But the powers of the Earth are often hidden. And despite the combined effort of geological scientists the world over, accurately predicting when and where an earthquake will strike is beyond us. Dr. Lin believes the enormous weight of 101 may have reawakened Taipei's dormant fault lines, increasing the threat of earthquakes, not just to the building itself, but to the entire city. Although Dr. Lin cautiously states that this theory is not yet scientifically proven, the circumstantial evidence seems compelling. Bigger earthquakes, and more often, since the construction of Taipei 101 began. But foundation engineer Dunstan Chen explains why he believes this hypothesis is fatally flawed.
That's actually at the beginning. For every high-rise building I built in Taiwan, we consider the weight you put that that the weight of the structure, okay, should be more or less equivalent to the soil you excavated.
The net change in pressure on the Earth as a result of 101 is nil. 700,000 tons of construction has gone up, but 700,000 tons of earth was dug out to build it. The unpredictability of seismic activity means that either way, we may never know for sure. And regardless of what causes the frequent earthquakes in Taipei, this man-made marvel is being built to withstand them. On the construction site of any super tall building, the difficulty of getting materials up to the action is one of the greatest logistical challenges. The primary tool for this on 101 is a series of 6 self-erecting construction cranes. The biggest, strongest, and most advanced on the planet, these cranes are able to shift thousands of tons straight up in a single day. But their most ingenious feature, and the one most crucial to the construction of a mega skyscraper, is their ability to self-erect, to grow with the building around them. To do this, powerful hydraulic rams lift the entire top mechanism of the crane. A new tower section is then placed in the gap, cross members secured, and progress resumes as normal with almost no interruption to workflow. Although concrete is one of the oldest and most widely used construction materials, it's incredibly heavy and, like a liquid time bomb, has to be pumped into position before it sets. These two factors pose a major challenge for construction workers on 101. The concrete they use here doesn't just have to get from the plant to the building, it has to get up the building as well.
Once you leave the batching plant, within 2 or 3 hours, you have to arrive on site and start pouring.
To do this, engineers develop concrete with specific levels of viscosity or runniness and specific drying times. This buys them valuable time and helps the powerful concrete pumps to work more efficiently. The result is yet another world record for 101. Concrete is pumped from ground level to 450 meters. That's higher than any other concrete pour in history. Construction reaches the 92nd floor in July 2003. Although nearing completion, the technological crown jewel of 101 is yet to be put in place. The tuned mass damper, the crucial windproofing mechanism designed to counteract the horizontal sway of 101's massive bulk. Although mass dampers have been used in skyscrapers before, they've never been this shape, they've never been this big, and at 380 meters, they've never been this high up. To be effective, the damper needs to be 0.1% of Taipei 101's total mass, a staggering 660 tons. Not even the awesome Taipei 101 cranes can lift something this huge and heavy. The ball arrives in prefabricated sections, which are then welded together on site. It's then hung from 16 10-centimeter thick cables and tuned to make it swing in exactly the opposite direction to the building.
When the building moved by the wind, it would go against it and balance it out real quickly, very much like the shock absorber of a car. And I think this idea has not been used in any other building that I know. So I think we're the first one to try that.
In principle, it works like a simple counterbalance. But in reality, things are a little more complicated and a lot more clever. To stop the damper from rocking either excessively or out of sync with the building, the ball is attached to a series of hydraulic dashpots, like mega shock absorbers, that stifle the ball's movement. If the damper experiences a particularly sudden jolt, such as an earthquake, the hydraulic resistance in the dashpots is strong enough to create a lockdown effect, meaning that the big golden ball in the sky will stay exactly where it is. If the mass damper is the technological crown jewel of 101, then the 60-meter pinnacle at the very peak of the building is the aesthetic equivalent. By late 2004, all major structural work has been finished on the main body of 101. Although this marks the successful completion of one of the most remarkable construction endeavors ever attempted, 101 is still 4 meters short of being the tallest building in the world. Successfully raising the pinnacle will assure them the title, but at 400 tons, it will also be a logistical nightmare. Nothing this heavy has ever been lifted in this way at this height. It's not just difficult, it's dangerous. A system of hydraulic jacks and geared cables lifts the massive structure from its base. Progress is painfully slow, but victory is the only option. Finally, after 14 days, the pinnacle is secured. Against all odds and against nature, the tallest building in the world is complete. Yet although this marks the end of one phase of the building's life, it is the beginning of another. Today, some of the world's biggest corporations boast offices here. And in peak periods, up to 40,000 people come in and out of the building every day. It's like a city unto itself, only vertical.
For a lot of people, until you see it, you don't believe it, nor do you understand it.
Many of the everyday functions we take for granted are complicated exponentially by the addition of height, making the operations of this mega skyscraper a mega challenge. Every minute detail of the building is monitored and accessed in here, the central control room. From the speed of every fan on every air conditioning duct to each of the 96 elevators, Operations Manager Jeff Shu and his staff can see and control it all. The security section monitors the focus, angle and zoom of each of 101's 520 surveillance cameras. The locks on even the most obscure doors are hardwired into the vast central brain of the security system. Staff continuously monitor the use and supply of electricity, the flow of water, the fire hoses in the mall, even the level of seismic activity. Every visitor is photographed and checked twice without them even realizing. Sucks in the equivalent energy as 6,000 regular homes. It's dependent on 2 designated city substations and has backup generators in case of failure. There's enough electrical cabling in 101 to stretch from Taipei to New York and back again. In case of fire, the equivalent of 2 Olympic-sized swimming pools of water is stored within the building to fuel the vast array of sprinkler systems. Stairways and corridors leading to the mechanical floor safety zones are pressurized to reduce smoke levels and are equipped with personal emergency kits, closed-circuit TV, and, perhaps most importantly, access to the outside world. On a building of this height, matters as simple as flushing a toilet pose serious challenges. 1 litre of water falling from the top floor of 101 will have the same impact as a house brick travelling at 65 kilometres per hour. Sewerage tanks on every mechanical floor contain, process and transfer grey water safely to the ground. The elevators are the fastest in the world. Travelling at 60 kilometres per hour, they go from level 5 to level 89 in only 37 seconds. Each carriage is pressurized to avoid ear damage, streamlined to minimize noise, and electronically balanced to ensure a ride so smooth that even a coin won't topple on the incredible journey. To clean each of 101's 17,000 windows, custom-built gondolas dangle workers off the edge of the building. They can only work when the wind is under 10 meters per second, and even then, the cables have to be hooked into the walls to stop the gondola blowing off track. The awkward angle of 101 means that an elaborate counterweight system has to be used so that workers can get close enough to the walls to work. To clean the entire building takes 4 teams of 2 workers 3 months. The job is so big that as soon as it's finished, it's time to start again. Inside and out, Taipei 101 pushes the boundaries. A unique-looking building that has changed the face of construction, design and engineering forever. The tallest building in the world, in one of the most hazard-prone places on the planet. Defying the powers of earth and wind, to go where no building has gone before.
It's really a very, very important building. It is a landmark, a benchmark.
Long after its mantle of world's tallest has gone, its achievement will remain. A symbol for the future of a proud island. A skyscraper that took on nature and won.